Let's look at the Chapter 5 review questions and their solutions. Number 1, Dr. Stats plans to toss a fair coin 10,000 times in the hope that it will lead him to a deeper understanding of the laws of probability. Which of the following statements is true? The correct answer here is letter C, that the fraction of tosses resulting in heads should be close to 1/2. So looking at letter A, it says it is unlikely that Dr. Stats will get more than 5,000 heads. This is a false statement, though, because even though we are doing this 10,000 times, which is many, many times, and we know that in theory it will work to be a 50-50 outcome, it's not unlikely that he won't get more. He could get 5,001, so something like that could definitely happen. Letter B, whenever Dr. Stats gets a string of 15 tails in a row, it becomes more likely that the next toss will be heads. Be careful with this one. This is an invalid statement. This is basically saying the law of averages, that this string of 15 will average out to be the next one. That next toss is still a 50-50 probability of getting tails. The string before it has nothing to do with it. Letter D, the chance of the 100th toss will be a head depends somewhat on the result of the first 99 tosses. Again, this is really related to letter B. If the first 99 tosses were all tails, it has nothing to impact that 100th toss. It's still a 50-50 chance. Number 2, China has 1.2 billion people. Marketers want to know which international brands they have heard of. A large study showed that 62% of all Chinese students have heard of Coca-Cola. You want to simulate choosing a Chinese at random and asking if he or she has heard of Coca-Cola. One correct way to assign random digits to simulate this answer is, the correct answer here was letter D. Do 2 digits simulate one person answer from 00 to 61 means yes, and the 62 to 99 would mean no. This would work because we're trying to say that 62% have, and we have 62 digits here. The remaining would have to be the no. Letter A does not work. A 1 digit simulates a person, meaning yes and no. If you did 1 digits, you would be talking like 10%, 20%, 30%, something like that. Because if it's a 62%, we do have to go out to actually have 100% or the 2-digit numbers. Letter B, 1 digit simulates one person's answer. Again, here we know if you were to use 0 to 6, meaning yes, that would be 60%. 7 to 9 would be 30%. We need to simulate 62%. Letter C is not correct. Using a 1-digit simulation of 0 to 9, meaning yes, that's a 100% chance that that would be yes, so clearly it does not work. Letter E is close. It's the 2-digit simulation. If you go from 00 to 62, in this case, this is 63 digits, and we're looking for 62%, so that's why that one does not work. Number 3, choose an American household at random and record the number of vehicles they own. Here's the probability model if we ignore the few households that have more than 5 cars. A housing company builds houses with 2-car garages. What percent of households have more than the garage can hold? So really the question here, what is the probability that our variable here is going to be greater than 2? So what we're going to look at are the 3s, 4s, and 5s. Based on that, if you add up those probabilities, we are going to get letter C. Number 4, computer voice recognition software is getting better. Some companies claim that their software correctly recognizes 98% of all words spoken by a trained user. To simulate recognizing a single word when the probability of being correct is 0.98, let 2 digits simulate one word. 00 to 97 mean correct. Now, the program recognizes words or not independently. To simulate the program's performance on 10 words, use these random digits. Right here, the number of words recognized correctly out of 10 is this. So let's perform the simulation of getting 2-digit numbers. When you do that, here's what you're going to get. So here are the 10 words, and the ones that recognize it correctly would be from 00 to 97. And of those, we see 9 of the 10 actually work. Therefore, we would include here. Now, you do have to think about, do repeats count or not? In this particular data set, we don't have any actual repeats, but if we did have repeats, they would count in this case. And the reason is this. The number assignment of 00 to 97 does not indicate a particular individual or particular item. It's just a general percentage. So in this case, repeats do count. And it's important for you to understand the cases where repeats do count versus don't counting. Again, if the numbers associated to our simulation are actual people or particular items, you can't repeat them because they've already been chosen. But if they're more general and they represent a standard percentage, then the repeats do count. In 5 through 7, we're going to use this setting. 1,000 students at a high school were classified according to both GPA and whether or not they consistently skipped class. The two-way table below summarizes our data. So we have our various GPAs and how many times they skipped the class. Question 5. What is the probability that a student has a GPA under 2.0? In this case, what we're going to be looking at are any of these students right here. And if we tally that up, it's going to be 255 students. This table, what you do want to do is recognize that there were 1,000 students. If they didn't tell you that, what you could do is just add these all up. Remember, in a two-way table too, they do recommend putting your column totals and your row totals here. So if we do look at it with the totals, we want those with a GPA less than 2.0, that's just 255 over the 1,000. So letter B was the correct answer for this particular one. Question 6. What is the probability that a student has a GPA under 2.0 or has skipped class? In probability theory, the one thing you want to remember is or indicates to add. So in this case, I want to find the probability that the GPA is less than 2 or the probability that they skip class. Now, if these are mutually exclusive or not will make a difference. So you always have to see if you're double counting. So you always have to subtract out the probability that here the GPA is less than 2 and at the same time they skipped class. So if we look at this and compute it, what we're going to see is that those students that have a GPA under 2.0 is the 255. And then we add those that skipped class many times, so in that case, the 110. Then we have to be careful because how many of those had a GPA less than 2 and they skipped class many times would be 80 of them are being double counted. So in this case, if you simplify it, you're going to end up getting that your answer is 0.285 because this is 285 and 285 out of 1,000 is where that comes from. Question 7. What is the probability that a student has a GPA under 2.0 given that he or she has skipped class many times? Now this is conditional probability, so we want the probability that GPA, again, is less than 2.0 given he or she skipped many times. So, a couple of ways to take a look at this one. If I take this, remember, I personally think taking this and just kind of doing a 90-degree turn to the right here would write it as the bottom of my fraction is I want those that skipped many times. So of the students that skipped many times, we know there's 110. This is a subgroup, so we are just looking at those students, 110 students. Of that subgroup, how many have a GPA less than 2.0? That's what goes on the top. That would be 80. So if you do 80 over 110, we're going to get letter E. Now, I do want to reference the formula sheet. The conditional probability formula on the formula sheet actually shows this, that they're going to say the probability of A given B is equal to the probability of A and B over the probability of B, which is basically exactly what we just did. So in our setup, we know we're conditioning on the skipped, so that's why we can find the probability of those skipping over the probability of this. If we were to do it this approach, we would just write it slightly different. The probability of B down here would represent the probability that many of them skipped. So the probability that many skipped would be 110 out of the whole 1,000. So here, when we write it out, we would have 110 over 1,000. And then on the top half, they want the probability that the GPA is less than 2 and many skipped. Well, that's 80 over 1,000. Well, if you simplify this, you're going to get exactly the same answer. Clearly, we're going to notice that the denominators on these would both cancel out. So just a different approach of looking at it, but you will get the same answer either way. The only difference is I personally like what I wrote in the red. It's kind of the shortcut of finding the subgroup because the conditional is a subgroup of the data. What I wrote here in the black using the formula, they still look at all of the data and they just simplify the fractions, so they don't actually put them into subgroups at all. Question 8. For events A and B related to the same chance process, which of the following statements is true? Now the correct answer here is actually letter E. And let's walk through the other choices as to why they don't work until we get to E. Now first, I think it's important to redefine mutually exclusive and independence. So I think looking at the OR formula on the formula sheet, keeping in mind your notation, by the way, the OR symbol is the union symbol for shorthand. Remember, and is the kind of looks like the N. That's the set notation for that. If you look at this, OR probability we know is plus, so probability of A plus B, but you always have to think about if things are double counted. This particular probability here, the probability of A and B, if the events are mutually exclusive, mutually exclusive means nothing in common. Sometimes our book will also use the word disjoint. So disjoint and mutually exclusive mean the same thing. If they have nothing in common, then to find the probability of A and B, our examples, let's say set A was I'm a male, set B, I get pregnant. What's the probability I'm a boy and I get pregnant? It's not going to happen. So if you're mutually exclusive, what you're going to notice is the probability of A and B would have to be 0. Okay, then you want to think about the independence. We said for independence, if we have probability of A and B, if two events are independent, means one does not impact the other, then we can say the probability of A times the probability of B. This is a nice shortcut for the multiplication theory. Again, remember, probability of A and B, if this says the word and if they're independent, means you can shortcut and multiply them together. If they're not independent, what you'd have to do is just look at the sample size and count and get a simple fraction from it, but you'd have to visualize the entire sample size. Now, the key between independence and mutual exclusivity is this. We know if the probability of A and B cannot happen together, means the probability of them happening at the same time is 0, and we call that mutually exclusive. Well, if the probability of these is going to be 0 and is mutually exclusive, then there's no way this probability formula up here for and can even exist. So the point is, if you are mutually exclusive, you cannot at the exact same time be independent. So mutual exclusivity and independence can never happen at the same time. If it's mutually exclusive, means the probability of the two things can't happen. Therefore, if the probability of the two things can't happen, you can't be independent. So based on that, letter A cannot work. It says here, if A and B are mutually exclusive, then they must be independent. They can't be. They can't be both of the two things. Letter B, if A and B are independent, then they must be mutually exclusive. That can't be either. So A and B are automatically knocked off here. Okay, letter C, if A and B are not mutually exclusive, then they must be independent. So what that one's going to say, if they're not mutually exclusive, so if we look at this, the probability of A and B, they have something in common. Maybe it's the two different samples would be set A is I'm a redhead, set B I have blue eyes. What's the probability I'm a redhead and I have blue eyes? Well, that could have something in common. So that's what it's saying here. They're not mutually exclusive. There's something in common. But it says here they must be independent from each other. Well, being a redhead and then having blue eyes doesn't mean that there must be independence. There actually might be some dependency between that. If I'm a redhead, I might be more likely to have blue eyes. So it's not must. That's what makes this one not a good answer. Letter D, A and D are not independent, then they must be mutually exclusive. Again, that word must is very strong. If A and B are not independent, means there is some dependency. Again, I'm going to go back to being a redhead and someone having blue eyes. Then it says they must be mutually exclusive. Well, it doesn't mean that they must have nothing in common. The only one that does hold is letter E. If A and B are independent, So we know if they are independent means the probability of A and B does exist. The probability of this happening is possible. Then they cannot be mutually exclusive. So if the probability of A and B can happen means they would be independent in this case, and then they cannot be mutually exclusive. Well, if the probability of this can happen means the probability of A and B being 0 can't also happen. You can't have probability of A and B give you a numerical answer and the probability of A and B giving you a 0 answer. That's two different answers, therefore it cannot happen. Number 9, choose an American adult at random. The probability that you choose a woman is 0.52. The probability that the person you chose has never been married is 0.25. The probability that you chose a woman who has been never married is 0.11. The probability that the person you chose is either a woman or has never been married or both is therefore about what? So let's write this formula out. They want here the probability that a person is either a woman or has never been married. So I'm going to write that out as the probability of being a woman plus the probability of never married. Just abbreviating here. Now I have to be careful. I have to back out the probability if you were a woman and never married. And think about that one. So the nice thing here, the probability here of being a woman is going to be 0.52. The probability of never married is 0.25. If I back out those women that were never married, I have to subtract out the 11 on that one. Therefore, we're going to come up with the answer here of letter B. Again, on the OR probabilities, we know we always need to think about if there's a double counting or if there is something the two events have in common. I always think of this third part. Sometimes this ends up being 0. If these two events are mutually exclusive or disjoint and have nothing in common, this will just phase out and become the number 0. But don't forget to think about it. It may come into play. And also remember, this formula is on the formula sheet if you need to reference it. Number 10, a deck of playing cards has 52 cards, of which 12 are face cards. If you shuffle the deck well and turn over the top 3 cards one after another, what is the probability that all cards are face cards? Now, in this case, you have to realize if there is replacement or no replacement. So here they are not replacing the cards, so we know every time we draw there's one fewer card in the pack. And we basically want to know that we have the probability of what our first is a face card, so probability of a face card, and we're going to get the next card, probably the next face card, and we draw the next card, probability of another face card. And here I'm using the word and for my probabilities. And means to multiply. We're in terms of this being dependent or independent, there is some dependency, but there is a little bit of dependency on here, obviously, because we're not replacing the card. But as long as we adjust for this probability, we can do this. So the first one, there are 12 face cards out of 52. We take one card out. There's only 51 cards in here, so we can use the multiplication theory as long as, again, we adjust this. There's only 11 face cards left, assuming that we did get one, and if we do that for 10 out of 50. When you do this and you simplify, you are going to get the answer is letter C. First free response, number 11 here. Your teacher has invented a fair dice game to play. Here's how it works. Your teacher will roll one fair 8-sided die, and you will roll a fair 6-sided die. Each player rolls once, and the winner is the person with the higher number. In case of a tie, neither player wins. The table here shows a sample space of this chance. So we have 8, we have 6, we have 48 options. Letter A. Let A be the event your teacher wins. Find the probability your teacher wins. So I'm just going to go to this table and actually highlight the points where the teacher's role is higher than the students and then add them up. And if you're going to do that, you're going to count that there's 27 out of 48 that work. Question B. Let B be the event. You get a 3 on your first roll. Find the probability of A or B. So let's write this one out in our notation. So we'll do the probability of A. I'm going to do probability of A plus the probability of B. And because this is an OR probability, I need to think about if anything needs to be backed out of probability, which would therefore have to be the probability of A and B. Now I'm going to go to the table, and they want to know the probability you get a 3 on your first roll. So that would actually be this particular one here. So from here all the way down, there's going to be 8 cases of that. Okay. Now, if we fill in and do this, the probability of A is going to be 27 out of 48, plus the 8, it looks like, out of the 48. But clearly we can see that we do have some double counting going on here. We have 1, 2, 3, 4, 5 of them that need to be backed out of here. So 5 out of the 48, and that is going to leave us with our answer of 30 out of 48. Now in AP Stats you can keep the answer there, but if we do simplify that one, it will get us 5/8. Okay, let's look at part C. The question here, are the events of A and B independent? Well, there's a couple ways you could go about doing this. Because in part B, the probability of A and B exists, means that they are not mutually exclusive. Now be careful, if you're not mutually exclusive does not imply dependency or independency, so that for that one. So what we'd want to do is our independence test. And I think the easiest way to do the independence is to test this. If probability of A and B, if they are independent, we know the probability of A times the probability of B is kind of the shortcut method we can use. Again, we can only use this formula if A and B are independent. So the easiest way to do it is to go on in here, find this probability, and then find these individuals and compare them. So the probability of A and B we already found. That was 5 out of 58, or 48, sorry. So we're going to do 5 out of 48. And we're going to compare it to the probability of A times the probability of B. Well, we already found the probability of A and we found the probability of B. So if we multiply those together, is this a true statement? When you do this and you check, these two are not going to be the same, so this is a false statement. You would do this, they're not the same answers, so we cannot say that they are independent. So we would say no, they are not considered independent because the right-hand side of this equation will not equal the left-hand side. And I caution you, be careful on this. Don't just look at the numbers and say, oh yeah, these two multiplied together are not going to get that. Change them to decimals and actually check. This one, for example, is the decimal 0.01 or 104,167. This, you're going to get something close, it's 0.09375. So if this was on an AP exam, I would actually compute these two sides and show that these do not equal, therefore they are not considered independent. Now the other thing for the independence test that we did learn, and I'll be honest, it's not my most favorite one, is we had said if the probability of A given B equals the probability of A, and then you check the probability reverse that of B given A equals the probability of B. If we could show that both of these two statements were true, it proved independence. You can absolutely use this other format again that I did initially. I personally think it's easier to remember. It makes more sense to me, logically, versus having to remember these two. I do recommend, though, being able to recognize this situation in case it were to show up on a multiple choice. But if you had a free response, I would recommend using this as an independence way to either prove independence or to prove not independent. Question 12. 3 machines, A, B, and C, are used to produce a large quantity of identical parts at a factory. Machine A produces 60% of the parts, while machines B and C produce 30% and 10% of the parts respectively. Historical records indicate that 10% of the parts produced by machine A are defects, compared to 30% for B and 40% for C. Draw a tree diagram to represent this chance process. Now, folks, I will tell you the AP Board will recommend if there's a probability question you're either struggling with, either try a tree diagram or try to come up with a simulation. This is a nice tree diagram, plus they want us to do that. So let's start with a tree diagram. And you're going to get our first branches. 100% of this is made up by the 3 machines. Now, if we branch out and we put on their defects, it will look like this. So what I'm using here is D for defect and D with a C as a superscript for the complement of the defect. So no defect, basically. So we have 10 and 90 make our 100, 30 and 70 make our 100, and 40 and 60. Now, remember the way to do the branch is what it's going to say is what if we choose machine A or we choose machine A and no defect and so forth. So and probabilities, assuming their independence, but for this tree, the and you're going to multiply. So I'm going to go ahead and multiply for all 6 strings and put their answers there. And when you look at all the answers, if you were to add all 6 of these up, it will come back to 100% of our probabilities. All right, part C. If we chose a part produced by one of these 3 machines, what is the probability it's defective? So in this case, they want us to look at all 3 of the machines, so really we're looking at the entire tree. And we just want to identify those that would be defective. So the defective ones that we can tell here are going to be this probability, this one, and this one here. If you add those up, the probability of this happening would be 19%. Question C. If a part is inspected and found to be defective, which machine is most likely to have produced it, given appropriate evidence for this? So the easiest way to do this is to actually compute 3 different conditional probabilities. Again, if a part is inspected and it's found to be defective. So we're going in assuming that this thing has been defective. So what we could do is we could find the probability of machine A given it was a defective part. We could do the probability of machine B given it's a defective part, and the probability of machine C given it's a defective part. So basically, given we have a defective part, what's the probability? It comes from machine A. Given we have a defective part, what's the probability it comes from B? Given we have a defective part, what's the probability it comes from C? So what I'm going to do for this one is be careful, this is conditional probability. So if you look at your conditional probability formula, again, I'm just going to write in general up here from our formula sheet, the probability of A given B is going to be the probability of A and B over the probability of B. So again, I always envision, I take this fraction and just rotate it 90 degrees to the right. That's why B goes to the bottom. That's how I remember it. Now, if we choose to use this formula, this is looking at the probability of the entire tree, all 6 branches. Now, I personally like to do conditional probability looking at the subgroup. So I'm going to show you how I can calculate this one with the subgroup and with this formula. It's the same thing. So here it's going to say, what is the probability we have A given that we are defective? So the probability that everything is defective is my total group. So what I'm going to do is I'm going to come on in here and I find all of those that are defective. Well, the defective is here, here, and here. That's our subgroup, okay? We already found the probability of defection, by the way, was right here. So the bottom, my new total, is only of the 19% of the group. Of those 19%, which ones am I talking about? I'm talking about machine A. So what I would do is put 0.06 on the top. Okay, that's how you can do that shortcut version. Now, if you wanted to use more of this formula, how they are doing it is actually going to be quite similar in this case because it's already in percent calculation. So if we were to write this formula, we would find the probability of A and D given the probability you're defective. So the probability you're defective, it's the same thing. It's still going to be these 3 circles, which is going to be the 0.19, and then the probability you're defective in A is going to be the 0.06. So you get the same number in this one no matter which way you think about it. So you can either look at the formula or you can think about doing your own subgroup. Now if you do this for all 3 of them, for B you're going to get 0.09 over 0.19, and for C you're going to get 0.04 over 0.09 or 0.19. Now this is also unique in that they all have the same denominator in this case, so technically you could just compare the numerators in here, so we know that the one with the most defects would be machine B in this case. Or what you could do is compute your, simplify these 3 fractions and find that the highest defect or the highest probability is machine B. Number 13, researchers are interested in the relationship between cigarette smoke and lung cancer. Suppose an adult male is randomly selected from a particular population. The following table shows the probabilities of some events related to this chance process. So we have the chance he smokes, smokes and get cancer, doesn't smoke and does not get cancer. Okay. Part A, find the probability that the individual gets cancer given he is a smoker. So this is conditional probability, so I'm just going to write this out as the probability he gets cancer, and I'm going to say given that he is a smoker. If we write this out, we know that it's going to be the probability of cancer and he smokes over the probability that he smokes. Now, do I have enough information for this one already? They actually did tell me the probability of smoking and cancer is right here, is 0.08. The probability that he smokes is right here, so this one's already nicely set up for us, is right this amount. If you compute that, you're going to get is a 32% chance probability for that to happen. Part B, find the probability that the individual smokes or gets cancer. So this is an or probability, so we are talking addition. So I'm going to do the probability that he smokes plus the probability he gets cancer. But I have to back out if there's any overlap or if it's not mutually exclusive. So the probability he smokes and has cancer. So if you look at the table to see what we have for this case, the probability that he smokes and has cancer, we do know. So that is, if we were to fill in this formula, a 0.08. The probability he smokes, we know, is 0.25. Now, the probability he has cancer, if we look at this, we don't actually have that information. Could we go ahead and figure it out? Possibly. So it's tricky if you actually go through this first route. So now I need to think of a different route of doing this problem that would make it easier. So I'm going to write this down. The initial question they wanted us to do was to find the probability that he smokes and has cancer. Now, because I know I don't have this value here and this is a hard way, maybe I could try doing a tree. A different way to think through it might be this. What about the complement theorem? If they want us to find the probability that he smokes and has cancer, what if I take, this is the same as saying 1 minus the probability of him not smoking and having cancer. So do I know the probability of him not smoking and having cancer? Yeah, it's 0.71. So if I do 1 minus 0.71 in this case, we will actually get the correct answer, which is going to be a 29% chance. So this one is tricky because at first you want to start using the OR formula. It doesn't work in this case, so we have to think of a different approach where the complement is really a nice way to approach this one to help us do it more easily. Question C. 2 adult males are selected at random. Find the probability that at least one of the 2 gets cancer. So there's 2 approaches on this one. The easiest approach for you to do is think about it this way. There's 4 different possible outcomes for 2 guys. So you're going to have cancer, cancer, no cancer for the first, cancer for the second, cancer for the first, no cancer, or no cancer, no cancer. Now, what they want to know here is what is the probability that at least one of the 2 gets cancer. So that would be at least one of them gets cancers would be here, here, or here. So if you could find those 3, you might be able to approach it. And you could do that one maybe using a tree. This one, whenever they say at least one of them gets cancer, or at least one of them in a group, the AP board likes this question. And the easiest way to address it is to find its complement. If you look at the kind of diagram I just made here of these 4 scenarios, they want us to know the answer to 3 of them. They don't want this answer. So it's easy if we find what is the probability of no one getting cancer and subtracting that from the whole of 1 will give us these 3 that we need. That is my one suggestion for anything that says at least one of these. That's the best approach to do and the easiest. So if we find 1 minus the probability of no 2 get cancer, we've got it. So we got to figure out what's the probability that they don't get cancer. So there's a couple ways you can come up with this one. What we want to do, the probability that patient 1 or patient 2 doesn't have cancer. Now I'm going to tell you a lot of the times the AP board, if they give you free response questions with multiple parts, they intend for you to use the previous parts to help you with that final question. And that's the case for this one. So what I would do is if we go back to part B, I'm going to write this down here under the green formula. This really was the probability that you smoked or you had cancer. Now we weren't able to use the green formula because we knew this part, this, but we didn't know this. Well, we just calculated this answer. This answer was 0.29. So I'm going to go back here and finish this formula over here. This is 0.29. So if we know this equation, remember we want to basically know the probability of not getting cancer. So what we could do is find the probability of one patient getting cancer. So if this patient gets cancer, to solve this, if you solve this for x, this is actually going to come out, and it's going to be that x is equal to 0.12. So that is the probability of this cancer happening. So what's the probability patient 1 and patient 2 don't get cancer? Remember, it's patient 1 and patient 2. Well, this would be 1 minus the probability that the 2 don't get cancer. Well, 0.88 is the complement. So if you get cancer, it's 12%, then 0.88 is you don't. Well, that's patient 1, and this is patient 2. So if you do 1 minus this, you're going to get 0.2256, which is actually the correct answer. Now, if you don't see the connection in part B, where you can compute, again, the 12% of getting cancer to back into the 88% you don't get cancer, you could make a tree for this one. And let me just show you really quickly. If you made a tree for it, you could have, for example, in this case is going to be an 8%. That's up here. Now, the only thing I could do is to back into what this would be. So I could do the 0.25 times something got me 0.8. This would have to be 0.32%. Okay. Well, if that's 0.32, then this would be 0.68. So could I get what goes in this box here? Yes. 0.25 times 0.68 would get me 0.17. Okay. Now, to get the other box, we already know they told us that it's 0.71. So from that case, you could add the 0.71, and we would have had to back into this 0.17. So backing into that 0.17 is a little bit tricky, but it would still work that way. Number 14. Based on previous records, 17% of the vehicles passing through a toll booth have an out-of-state plates. A bored toll booth worker decides to pass the time by counting how many vehicles pass through until he sees 2 with out-of-state plates. Describe the design of a simulation to estimate the average number of vehicles it takes to find 2 with out-of-state plates. Explain clearly how you use partial table of random digits below to carry out your simulation. So let's first start by assigning the numbers. So I would say let's do 0, 0, 2, 1, 6 are going to be our out-of-state plates. And then we are going to have 1, 7 to 99 be our in-state plates. And that'll account for our 100%, and all the digits would be covered. Now, do know you could have done this saying 3-digit numbers. If you did 3-digit numbers, you would have to say something, maybe you would say from 001 to 017 would be out of state. And then 018 to 100 would be in-state. And then from 101 to 999, you would ignore those. Now, it's not going to work with the data they gave us to do 3 digits. It's better for 2, but technically you could. Now, after we do that, our next step is we're going to use table D, and we're going to start at the beginning of that table. And we are going to include repeats in this one. So it's important to make note of that because the numbers that are assigned do not represent individual cars or people. They're not one thing. They're a standard percentage. Repeats are included in this. And we're going to do it until 2 out-of-state vehicles show up. And then the last thing we're going to do is we are going to repeat this many times. And then part B wants us to go ahead and perform that simulation. So if we do that, they want us to do it 3 times. So the first simulation for this one, what we're going to get is we have 41, 05, and 09. And these two are going to be our out-of-state cars, and that will be it for that. Now if we do our second simulation, and we go through that, that one's going to take us actually 14 tries all the way to 11. So we are at a total right now of, for this one, 3 tries, 14 tries. Now in our third simulation for this one's going to take us, it looks like, about 13 tries, and here's what we get. That one did take us, it looks like it was 13 tries for that one until it happened. I hope you found this review helpful. Please let me know if you have any questions on this chapter material.